um, 8 years ago already. And also because my very first school was here, well, in Rua Pamplona, 21 years ago. I was undergrad. It was very important, that school, for me. So I think it's really changed my career. I will not tell you why today, maybe on Friday. Okay, so I'll be talking this week about dark matter. And let me first, okay, the question is, what are the building blocks of the universe? So this was discussed last week by Christophe. So I think he extensively presented the standard model, so all the elementary particles. We have the quarks, leptons, so charge and neutrinos, the force carriers, gluon, photon, Z and the W, and the Higgs. So it was discussed last week. Okay. And the standard model, Lagrangian, right? So we have the kinetic term for gauge bosons, for fermions, the Yukawa interactions, and the Higgs potential, right? So that was what Christophe was discussing last week. So the question is that, are we done, right, with the particles? Is that the last? Are we covering the whole if you want, the whole universe, the whole energy density of the universe with the standard model? Do we have to go beyond the standard model? And of course, the question is not. There are several questions that are still unanswered in the standard model. For instance, we know that the mass of the neutrinos, the standard model predicts the mass of the neutrinos exactly 0. We also have the hierarchy problem of the Higgs that we discussed by Christophe, and dark matter, right? So I'm Colombian, so at some point I have to have an arepa. So if you think these are the whole energy density of the universe, the standard model basically is this baryonic matter, so, and it represents only 5% or so of the whole energy density budget of the universe, so 5%. 25%, so 5 times more, is in the form of dark matter. And the rest, 70%, so the big majority of the energy density now is in the form of dark energy. So maybe cosmological constant, we are not sure. It's a very difficult question to tackle from the particle physics perspective. So the idea here in these 5 lectures is to discuss the dark matter, right? So what the dark matter is, what are the motivations of the dark matter, what are the models, really from the model building point of view, and how can we possibly detect this elusive dark matter. So already, Kafir discussed some models on Friday in particular. He discussed the misalignment mechanisms of fuzzy dark matter. So the idea of this series of lectures is, okay, the introduction first. Then I will try to convince you that dark matter exists. Some criteria for dark matter. Right, so what properties has to fulfill the dark matter? We discussed a bit about the thermal universe. Thermal universe and particle cosmology. Cosmology. Our beloved Boltzmann equations. Boltzmann. Hot relics, neutrinos in particular. WIMPs. This is for you, Giovanni. They put a heart here. So it's a difficult story for WIMPs, not for you. It's a complicated story with WIMPs. So let me put an arrow here. So it's a story of love and, yeah, you will see. And deception, yes. It's a complicated relationship with WIMPs. So WIMPs are thermal candidates. WIMPs. So it's called more on thermal dark matter. It will take like 10 weeks. Non-thermal, and of course non-thermal as well. And like on Saturday, on Sunday, detection. Yes, that's will be more or less the idea. And of course, non-thermal is a huge thing, so there, we'll see what's your interest and how fast or how slow we're going. So bibliography, so I may upload these notes. They are kind of crappy, but I can give you some bibliography if you want. So okay, your Bible or Quran here is Colban Turner. So this book, The Early Universe, is kind of old. It's from the 90s, but I think it's still a super reference. Also, if you want new things, we have Rubakov and Gorbunov. The book is called Introduction to the Theory of the Early Universe. It's from the 2017. So this is 90s. This is 17. There's a book I like a lot from Profumo. It's very, Italian way. No comment. Profumo. An Introduction to Dark Matter. Well, maybe I should write the title as well. And there's a new book by Mambrini. Jan Mambrini. So Profumo is an introduction to particle dark matter and Mambrini's particles in the dark universe. So this is from 2021. Profumo is 17. Yeah, you can take a look if you want to go deeper. Okay, so the idea, as I told you, is to study. I will try first to convince you about the existence of dark matter, but it's not yet. So dark matter exists. So let's tackle this point. So why do you think dark matter exists? So first, kinematics in galaxy clusters. So, and here we have Zwicky. This is CK, Zwi, CKY. 1933. So the idea is very simple. In principle, the idea is to reconstruct to measure the matter in a cluster of galaxies. So you can do that in two ways, at least. So you can measure the total luminosity, and from the luminosity you can reconstruct the mass using the mass function. And you can also try, measure the kinematics. If you know the kinematics, you can try to reconstruct the gravitational potential. From the gravitational potential, you can extract the total mass, and you compare the two measurements. So from the gravitational potential, you can compute this, the nabla square of the gravitational potential, and it's like 4 pi g Newton rho, where rho, the gravitational potential, rho is the energy, the total mass density. And that's what Zwicky was doing back in the 30s, so like 90 years ago. So he computed the luminosity, the total mass coming from light, right? Measuring the light in these galaxy clusters, and computing the visible mass. The visible mass with the luminosity, and computing the total mass with the kinematics. And what he found is that the visible mass, the mass visible, was much smaller, the gravitational mass, if you want. the gravitational mass, right? So the visible mass was not enough to hold the whole cluster together, right? So we have, okay, and this comes from cluster, right? So typical scales is, say, whatever, is a megaparsec, right? Clusters is typical scale, typical size of clusters is megaparsecs. Okay, that's one probe of dark matter, but also, I mean, level of clusters, but we also have some evidence at the scales of galaxies, so much smaller scales, galaxies. So we have galaxies. And galaxies is more like kiloparsecs. And now we have Vera Rubin in the 70s. And what she was doing is, it's fine, right? I don't have to switch off the light. I think it's fine. Measuring kinematics in galaxies, right? So this was a cluster, in particular, this was the comma cluster. So he was measuring the kinematics in spiral galaxies, right? So the idea is to take stars within the galaxy or even other bodies, again, gravitationally bound in the galaxies, rotating around the galaxy, measuring the circular velocity. So here, for instance, this plot is the circular velocity of gravitationally bound objects rotating around the galaxy as a function of the radius in kiloparsecs, right? So it's a typical galaxy. And what you expect is that the velocity, you can compute the velocity, it's something like g Newton times the mass over r, the square root. So the total mass enclosed in a sphere of radius r, something like this, that you expect. So what you expect is that when you're inside the galaxy, this guy has to go up, right? Have to rise. But interestingly, when you go out of the galaxies at very large radii, you expect this to go like 1 over r. Yeah? And this corresponds to this line here. I'm colorblind, so it's very difficult for me to follow this red point. So outside the galaxy, that's what you expect, like to drop the velocity like 1 over the square root of r. However, that's not what you're observing, though. That's what Vera Rubin observed. She observed more like a, can you see the pointer? I don't, okay. So like a flat behavior of the rotation curve. Okay, slightly better, thanks. So that suggests the existence of an extra component that you're not seeing, so a dark halo of dark matter. So if you define, for instance, here, like the energy density, sorry, the mass density like the mass over r cubed, right? You can rewrite this like Gn rho r squared, something like this. And if this thing is constant, that means that r, that the mass density has to go like 1 over r squared, right? Why? Just because what you're observing is like a flat behavior of the curve, rotation curves at the level of galaxies. So the idea is that around your galaxy, so here, for instance, you have, again, don't see. No, it's fine. So you have your galaxy, you have the ball, you have the disk, right? So say a few kiloparsecs or so, the luminous mass, really the interstellar medium, all your galaxy, and around you have like a kind of spherical dark matter halo, much, much larger than the visible matter in the galaxy. So we already know how it should behave. It should be a large distance should behave like something like this. Of course, what the exact parameterization of this mass, the density of the dark matter halo, if you want to have more detail, you have to go to M-body simulations, and there are M-body simulations. There are different profiles that are favored by M-body simulations. And I just want to mention one in particular. So it's the NFW, just for you to give you an idea. Thanks, sorry. This mass profile. So it's something like where this rho S and RS are just scalings, right? So it's very simple profile, right? So different kind of slopes in the inner part and very far away from the center. And I just mention in particular this profile because I think it's kind of, maybe, I don't know if it's a favorite, but it's very favored by different embodied simulations, both dark matter only and aerodynamical simulations to take into account invariance. But the main reason why I'm mentioning this profile, because in NFW, N refers to Navarro, Julio Navarro from Argentina. F is from Carlos Frank. He's Mexican. W is white, but he's not Latin American, so I will not mention him. He's German, I think, German, British. Okay, again, so we have evidence from clusters of galaxies of megaparsecs, galaxies, so smaller scales, kiloparsecs. There are other evidence, for instance, the bullet cluster. It's fine, fine. What? Out. And maybe you are familiar with this. Could you please? No, I'm kidding. No, it's fine. Maybe you have already seen this image of the bullet cluster. The idea is you have actually two clusters. They collide, right? They collide. They went one through each other. And the image here is the cluster after the collision. So they went one through each other. So that's what you can see. Okay, these are just scattered galaxies, right? So you can try to reconstruct the gas. So in a cluster, the bulk of the matter is in form of gas. So you can reconstruct the gas with X-rays. So and from X-rays, you can see that most of the gas is here and here. So after a collision, of course, the gas is very hot. It's emitting X-rays, so you can see, like the shock waves after the collision. So the important thing is that the gas basically is here and here. So from X-rays observations. Also from gravitational lensing, you can reconstruct the gravitational potential. So these lines, these contours correspond to isocontours of the gravitational potential. So you have two maximum or to minimum in this well, so one here and one here. So this is telling you where the bulk, the most of the matter is. And you can see that the most of the matter is here and here, and it's far away from where the gas is, where baryons are. So that also implies that there's some other form of matter which is gravitating, right, but it's not emitting light. So you understand that this kind of understood saying that here you have, basically here you have the dark matter halo, one here and one and the other, and it's displaced after this collision, right? So that's the bullet cluster, again, scales of megaparsecs or so, but we have more evidence, so it's basically the same thing. You can have also from gravitational lensing. Yeah, so you can use lensing for reconstructing the total mass, right? So basically we're here, we have the lens here, and you're observing some galaxy like far away behind the lens. With gravitational lensing, you can reconstruct the total matter, not only the visible matter, and you can see that in order to explain the lensing that you observe, you need much matter beyond what you expect from the visible, the matter that you can reconstruct with pure light. So also using gravitational lensing, you have evidence of the existence of dark matter. If we go back to clusters, hot gas in galaxy cluster, basically the idea is the same. So clusters are basically filled by hot gas that is not falling into the galaxies. So we can observe this gas with X-rays, this hot gas with X-rays. And from the hydrostatic equilibrium, you can reconstruct the total mass, the total gravitational mass, and therefore, again, you can compute, or you can try to measure what's the visible mass, you can extract what's the total gravitational mass, because of this hydrostatic equilibrium, you have that there's a difference in mass. The gravitational mass is you're measuring that it's much bigger than the visible mass. Therefore, dark matter, blah, 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 blah. Same thing. Structure formation. So other questions, comments? Yes.
It's very low.
Can you talk more about the NFW profile? Just by looking at it, it seems at large R, I have a 1 over R cube behavior. Seems counterintuitive. So I would like to understand the physics better. Why not 1 over R square?
Yes, okay. This was like a very naive approximation. However, it turns out when you do the proper body simulations that, I mean, this fits typically well what you see in body simulation. Yes, okay, but you're completely right. So this goes from 1 over R to 1 over R cube. There's, of course, like a sweet spot where you have R square. But yes, I agree that this sounds not very intuitive. Yeah, but okay, so you have this one. I think this I don't know if it's the favorite, but it fits well observation, the N-body simulation. They also have the Einasto profile, but Einasto is Dutch. That's why Einasto. Isothermal profile. So there are several.
So maybe we can discuss more in Q&A, or personally I can come by if you would like.
Sure.
Thank you.
Yeah, we have the Q&A. Yeah, so I forgot to tell you. Okay, we can ask at the end of the lecture during the Q&A, but please stop me if you have any question. I mean, after all, this is for you guys.
When they measure gravitational mass by all these different methods, they get the same. Like they obviously get different from the visible mass, but in all the gravitational mass methods, they get the same or not?
The same. I mean,
the same like mass distribution or total mass or whatever, like only because of the gravitational effects.
Yes.
Like if you measure it by kinematics or by gravitational lensing or whatever, the same thing, you get the...
Okay, yes, so but I mean, I think it's basically the same method. It's right, here you really compare light versus kinematics, right?
Yeah.
Yeah, so it's not that there are different methods to extract like the gravitational potential.
Okay, but one is by the curvature of light and the other is because of the movement of the planets or something like that, or not? Like lensing would be because of the curvature of the light moving.
Yes,
right?
there are different. Yes, of course, these are different techniques. For instance, here really using gravitational lensing, right?
Yeah.
But so I think your idea is to use gravitational lensing here, but on top of that, try to use the kinematics of this galaxy here. But I think you cannot do it because this galaxy here is behind, so I'm not sure if you really have access to the kinematics.
Okay.
Kinematics here.
Yeah.
Okay, I see. I think in principle this can be done, right? I don't know. Yeah.
Yes, yes.
All these different measurements of the dark matter density, do they agree?
Well, they should agree, yes, I think, inshallah. No, but I think at this point here, I'm not trying to extract for instance, the density or something like this. For that, we will use more the CMB. I just want to, at this point, what I want to motivate is that we have different observations that encourage us to go to the dark matter. They appear at very different scales. So scales of parsecs, kiloparsecs, sorry, megaparsecs. We'll see for structure formation where the CMB is really at the cosmological scale. And okay, so different scales in length, right, in distance, but also in time. Because, okay, so these are a very low redshift, but when you saw this structure formation or read the CMB, it goes to much higher redshift. So we have evidence of the existence of dark matter at different scales in length, in distance, but also in time. Yeah, that's the idea. Yep. So a couple of words about structure formation. So we know that at the moment of the CMB is basically homogeneous and isotropic, so with very small inhomogeneities of order 10 to the minus 5 or so over rho 10 to the minus 5 at CMB. However, the universe now is well, we have galaxies, we have clusters, we have streams, we have voids. So how can we go from a very homogeneous to the universe we observe now? Okay, so we know, okay, that was the moment of the CMB. We know how these perturbations grow. So these perturbations as a function, okay, as a function of the scale factor, as a scale factor A, they grow. As a log, if the universe is dominated by radiation, and they grow linear if it's dominated by matter, right? So a logarithmic growth basically is no growth, right? It's not particularly fast, it's just logarithmic. So if we want to understand, if we want to reproduce the observations of large-scale structures, we have to go early enough into the matter regime to allow inhomogeneities to grow, to enter the nonlinear regime. And therefore, we need extra matter, in particular, dark matter. So to understand the growth of structures, so to reproduce the observations, if you want to do, for instance, the n-body simulation, you have to introduce the dark matter, and dark matter has to dominate early enough to have the growth of structures. Yep. Okay, last but not least, CMB. Okay, CMB. This is amazing, the CMB. But where it's, yeah, it's far from trivial. Kafir already discussed a little bit about it. So if you want to understand the dynamics of CMB, I mean, it's not a course, not 5 lectures, it's more like a semester, right? So it's, however, I mean, we know, we have seen this, I think, before. So it's the map of temperature by Planck, 2018. So what here is showing you, I mean, what we learned from CMB, that is basically super homogeneous. However, there are these very small inhomogeneities of the order 10 to the minus 5. So here's a map of the whole sky. The blue dots correspond to points where you have slightly colder patches of the universe, and the red is the opposite, where the temperature is slightly bigger. And this, again, these homogeneities are 10 to the minus 5 or so. So this can be very well understood in the framework of lambda CDM. So where, you can say there. Okay, where this cosmological model where you have a cosmological constant, lambda CDM, DM is dark matter, surprise, surprise, and C is cold. So in particular, we need this cold dark matter. Okay, so from this picture, we can extract the temperature fluctuation in a function of multiples. So the dynamic is very complicated at the moment of the CMB. You know, you have electrons, protons, neutrinos, photons, and dark matter that are roaming around. Electrons, protons, photons are bounded. You have Coulomb scattering, very efficient Coulomb scattering. You have Thomson scattering. Dark matter, however, dark matter is free. It can collapse gravitationally. But all these fluids, so these two sectors are gravitationally coupled. So understanding the dynamics of these sectors allows you to have this kind of behavior. And from this, in particular, from this, you can extract a lot of information. For instance, the different height of the peaks, the relative height, the position of the peaks is, again, like it's a proof of the existence of dark matter. And in particular, you can extract, basically, that the abundance of the dark matter is basically 5 times the total energy density or total abundance of baryonic matter, baryons, from the CMB. Yeah. And with this, we can basically go back to this thing. So from CMB, you can extract the total energy density and how it's distributed between baryons, between dark matter, and between dark energy, right? So going back to the beginning. So again, so I gave you all this number of evidence of dark matter, and I just want to emphasize the 3 points that I told you before. So we have evidence of dark matter at different scales. Scales of clusters, scales of galaxies, so kiloparsec, megaparsec, but also at the cosmological scales, so the behavior of the CMB, the formation of structures.
Again, can you please explain again how they extract the dark matter density from the cosmic microwave background?
Yes. I cannot give you much more details, but basically it's studying the structure of the peaks. So where the position of the peaks and what's the relative height of the peaks. Yes, I told you the dynamic here is fascinating, but I mean, it's difficult to explain in a couple of minutes. You really need a course devoted to CMB. Yeah. So we have so evidence, I was saying, at different scales, right? But different also redshifts, right? So at low redshift, but also a very high redshift with the CMB and structure formation. And the third thing, I forgot. I don't have it here. Okay. Fine. Questions, comments? Okay, criteria for dark matter. So we're kind of convinced that dark matter here, but what are the properties of the dark matter? Criteria. So what conditions a viable dark matter candidate has to fulfill? First, we know the density from CMB. So from CMB, we know that this omega dark matter H square, omega is basically this 25%, right? So the total energy density stored in dark matter over the total energy density of the universe. So the universe is flat, so this is a critical times H squared. H is a reduced Hubble constant. So this is basically 25%. H is 0.7, give or take. So this measured by Planck is 0.1198 plus or minus 0.0012. This comes from Planck. Oops, I forgot. Okay, this is relic abundance. Planck, 18. Okay, this is an important piece of information, the relic abundance of dark matter, which is basically, what we say that, 25% of the total energy density of the universe, 5 times more energy density with respect to baryons. Okay, dark matter is matter, right? So mass. What do we know about its mass? So this is interesting. So the mass, it has, okay, that was first discussed by Kafir, if I remember correctly, on Friday. So we have some evidence of dark matter at the level of galaxies, so small galaxies, so dwarf galaxies. So we know, I mean, to dark matter to have an effect, we have to have de Broglie wavelength smaller than the typical size of the smaller objects where we can feel the evidence of dark matter. So we can compute the Broglie wavelength of the dark matter, which is basically H. H now is Planck, right? So this H and this H are completely different, as you can see. So the de Broglie wavelength is H, Planck H over momentum. Momentum we want dark matter to be cold, so we want to be non-relativistic at present. At formation as well, so it's mass, dark matter, P is times the velocity. Momentum is mass times velocity. So from here, we can extract an lower bound for dark matter. Take into account that typical size of dwarfs, it's kiloparsecs, so dwarfs. It's like, say, order kiloparsec. And typical velocities of objects inside, so in particular, velocity of dark matter is like hundreds of kilometers per second. Typical velocities, right? So give or take an order of magnitude. So say kiloparsec scale and velocity of order hundreds of kilometers, this kilometer, sorry, kilometer per second. So using this piece of information, they can extract a lower bound of the dark matter, which is around 10 to the minus 22 electron volt, using these numbers. And we already saw this number on Friday with Kafir, when he was discussing his model of scalar dark matter. Right, so this can only, well, this is particularly important for bosons, for bosonic dark matter. For fermions, we can extract a much stronger bound. Because fermions are fermions. Yeah, fermions mean that, well, fermions have to fulfill the Fermi exclusion principle, right? And the idea is that, sorry, if dark matter is very light, you have to have a lot of particles, right? So, for instance, in a given dwarf galaxy, you can compute what the total dark matter mass there. The total, if you know the mass of each of these particles, you can compute what's the total number of particles of dark matter that have to be there. And if there are fermions, you have this Tremaine gun. Limit, this is 1979. That limits, so now that fermionic dark matter has to be heavier than more or less order 10 electron volts. Just because of the Pauli blocking, that Pauli blocking is, well, blocking the phase space. So those are very general bounds on the dark matter mass. So 10 to the minus 22 around for fuzzy dark matter in the case of bosons. If you kind of fermions, you have like order 10 electron volts, right? This, okay, this is some information. However, I mean, we still, the range of mass is huge, right? We want the dark matter, okay, to be heavier than this. But what's the upper bound? I mean, it's not clear. We typically want dark matter to be a fundamental particle, so better if it's lighter than the Planck mass. But that means that if you make if you plot the dark matter mass, it will be something like this. You go blah, blah. Here you have like the Planck mass. And so 10 to the, in electron volts is what? 10 to the 18 plus 9. Thanks. 27 electron volts. And what I'm stopping here is, well, I don't know. I want it to be a fundamental particle. However, does it dark matter has to be a fundamental particle? No. So it could be, I don't know, some relic at the Planck scale. You can think about the primordial black holes or general black holes. So the mass could be much heavier, much higher than the Planck mass. So it can go there until Argentina. But at least if we want dark matter to be a fundamental particle, so this is basically the range. So 10 to the minus 22 electron volts. So for bosons, so you have to be in this range. If you're fermion, you have to be more or less here, like 10 electron volts or so for fermions. But just want to emphasize that the parameter space is huge, right? We have like 50 orders of magnitude. So imagine the experimental challenge. So you want to look for a particle Why a particle? Well, because we're particle physicists, so we assume that it's a fundamental particle, a single particle, with you have like 50 orders of magnitude in mass. So the experimental challenge, I mean, is huge. And it's, okay, we only have here a single dimension, so the mass. But of course, we as particle physics want dark matter to couple to standard model particles. So why? Because we want to complicate our life, right? So we want to couple to electrons to have bounds from lab, for instance. We want to couple to quarks, to produce it at colliders, to have direct detection, to have indirect detection. So you just want to emphasize that if you imagine the parameter space is huge, right? So that 50 orders of magnitude in mass, but it's not a single dimension because you have another dimension for coupling with electrons, with muons, with quarks, with Higgs, why not, right? And of course, if you have this, let's focus on the mass. So if you have all these 50 orders of magnitude, of course, there's not a single mechanism to populate the dark matter. So this piece here, say, was discussed by Kafir. This is basically fuzzy dark matter. ZZ. Fuzzy dark matter. Then typically WIMPs are more or less here, WIMPs, standard WIMPs. So if you want, you still remember the neutralino, basically here in the GV to TV scale. However, general WIMPs could be, I mean, general WIMPs, let's say, until here. Maybe here's 100 TVs, but this could be up to 10 to the 10. You can imagine viable WIMPs at the scale of 10 to the 10 GeVs, so 19 electron volts. You can also, there are very, this ballpark where you have MEV dark matter, some MEV to GeV is favored by, for instance, by SIMS, so by elders. This piece here is more by cannibals, cannibal dark matter. It's not my fault. Axions are microelectron volts, well, here. Microelectron volts is axions, typical QCD axions. Yes, okay, we have different mechanisms. For instance, FIMS, you can start at the KeV scale and go all the way here. So non-thermal dark matter, FIMS. Okay, it's a mess. There are different kind of mechanisms, very different, both thermal and non-thermal, which give rise to viable dark matter candidates in this huge parameter space, right? Just in mass, just thinking about the mass. Yeah? Okay. Let me erase this artistic drawing. Other property. Dark matter is, okay, matter, so we have mass, but it's also dark. Neutral. So there are bounds on the charge, on the electric charge of dark matter. Because after all, if dark matter is kind of low, light enough, it can create bound states with electrons. So there are bounds on the dark matter mass. So Q, charge, electric charge, sorry. What's happening here? Q. has to be smaller than 10 to, and it depends on the mass. Actually, what is bounded is the ratio Q charge over M. So the electric charge has to be more than 10 to the minus 6 or so if the dark matter mass is 10 GeVs. But if you go to heavier dark matter mass, you relax a bit the bound. So the electric charge has to be smaller than 10 to the minus 4 if the dark matter mass is 10 TeV now. Yeah, so you can have a milli-charge dark matter particle. Yeah. So that means that the interaction with photon is very suppressed. And it's important because we want dark matter to be non-dissipative. We do not want it to dissipate, to lose energy with photons in particular, because we want the dark matter halo to be kind of spherical. So if you have dissipation, you will go from a spherical halo to like a disk, like with baryons. So galaxies are not spherical because you have dissipation. They collapse to a disk, so we want to avoid that. So it's natural to expect very small couplings to, electric charge in particular, so very suppressed couplings to photons. Okay, so effectively dark matter is dissipationless. Dark matter is cold. And what does cold mean? That it has to be non-relativistic. At the moment of structure formation. Yeah, that means at the matter radiation equality. So when the temperature of the matter radiation equality, so if you dark matter and radiation equality, that's basically is order one electron volt. And again, you want it to be non-relativistic to have the linear growing of structures that I wrote here and I erase. What else? So we know the density, very weak limits on the mass, on the electric charge. It has to be cold. It has to be collisionless. And we have bounds on the elastic scattering cross-section of dark matter. So you can think dark matter as billiard balls. So you can have elastic scatterings. So dark matter into dark matter. Really billiard balls, huh? Elastic scatterings. For instance, you have inside of this kind of cross-section, actually over the dark matter mass from the bullet cluster, for instance, you have collision of clusters of galaxies. We saw in the picture that we expect dark matter to, we saw that dark matter just pass through, right? So dark matter cannot interact with itself in a sizable way. So from the bullet cluster, we know that the sigma over m, so sigma again is the elastic scattering cross-section, has to be smaller than order 1 square centimeter per gram. And we are happy because we are very familiar with these units, right? square centimeter, fine. Gram, fine. 1, perfect. However, I can just change the units to more particle physics units. This is 1 barn over GV. So, for instance, if dark matter is 1 GV, like proton, that means that its this elastic cross-section is 1 barn. 1 barn is huge, right? Remember, at LHC, we're used to picobarn, femtobarn, attobarn. This 1 barn, this is ridiculously big. So collisionless, I don't know. I mean, collisionless, of course, at which scale, right? At level of galaxies, of clusters of galaxies, yes. However, keep in mind that this cross-section is far from being small. Yeah. So collisionless, well, that's what we say. That's collisionless for astrophysicists, maybe. And upper? Yes. 0.
Okay,
No,
lower bound.
no.
Yes.
Yes, of course. Okay, you can. Okay, yes, that's fine. Yes, you can have gravitational self-scattering, which are 0. Yeah. Yeah, you typically assume that this is 0. Huh? I mean, for WIMPs, you typically put this to be 0, and that's it. But it's true that gravity is inexorable.
Here, question.
Yeah.
Does kind of the accretion disk of black holes provide any bound in these kind of collisions?
Accretion disk?
Yeah,
black holes?
because you could find kind of collisions on that stuff with a lot of energy, right? Can we observe anything related to dark matter there?
But wait, you don't want here your black holes to be the dark matter. You have the accretion disk, and you have on top of that the dark matter?
Yeah, in the dark matter kind of having collisions in the disk accretion.
And? Do you want to have like annihilations?
Yeah, I mean, I would like to know if there is any kind of bound to this stuff or like that due to observations on that.
I don't see how you can.
No, okay. Okay.
Yeah.
I think people are starting to make projections, I think, from gravitational waves using dark matter around black holes or merger of neutron stars. I think they can constrain, but currently experiments cannot, so we have to wait for further experiments.
Mm-hmm. To test this self-interaction?
Yes, yes. I think they can. They are studying this possibility.
Okay, thanks.
It's a good topic for the discussion session.
Yeah.
Maybe you should read the paper and tell us how did they get these constraints.
Yes. Good morning. First of all, I'm sorry if this is a basic question, but I was wondering, why does dissipation must imply that you cannot have a sphere and you must have a disk?
That's just conservation of momentum, no? If I'm not mistaken. Yes, so you want to avoid that's I'm not sure now. But, yeah, who help?
Yeah, it can release energy. Yeah.
Marcus has something to say?
I think I just wanted to say the same thing. I don't know the actual mechanism for making a disk, but if you start with a spherical cloud and the particles really don't interact, then it's pretty clear that they're just going to be mixing with each other, moving in each other's potential, and remaining spherical. But I think that's basically what is said over here, maybe.
Just a comment. There is a very simple exercise of classical mechanics. If you have a system with gravity, you impose conservation of angular momentum and kinetic energy, you have a spherical symmetry. But if you relax energy conservation, but impose angular moment conservation, then if you just minimize the energy, then you solve the equation, you see z equals a 0. This is basically a disk. So it's
Okay, yeah.
very
Yeah, that's what I have in mind, but I have never done
straightforward,
the
yeah.
exercise. Good. An exercise for tonight. No USP tonight, sorry guys. Yeah. So collisionlets in these big quotation marks and want to be long-lived. And why long-lived? I mean, again, we have seen the effects of dark matter in basically in all the epochs of the universe. So it has to be either completely stable as a particle or long-lived with a lifetime much bigger, much larger than the age of the universe. The tau of the universe, which is basically 10 to the 17 seconds, right? So long-lived, maybe stable. So dark matter could decay, right? You can have decaying dark matter. However, yes, with a very long lifetime. So other questions or comments at this point? Because now I want to discuss the thermal universe. Yes, I still have time. Yeah.
How do you know that? I mean,
How do I know what?
the longer lived, the time that it must live, because I mean, you could have dark matter, decaying in dark matter, decaying in dark matter, decaying in dark matter, and I mean,
like multi-components, you mean?
Yeah, yeah. But so how do you say that? Oh, this is the time that it must live. You know, how do you measure that?
But this, so your idea, you have like a heavy guy of the in the dark sector that decays into two light states, and these light states are really the dark matter.
Yeah, the entire sector of dark matter. But I just curious about how do you have sure that this is the...
Okay, so if you have a single component, it's trivial, right? You understand that?
Okay, yes.
Yeah, suppose you have several components, so you have one heavy guy that decays into two dark matter particles.
Yeah.
But then these two guys, if it comes from a heavy guy, will be relativistic.
Ah, see.
So
you go to the non-relativistic stuff.
Yeah, so this could happen at the very early universe. So the heavy guy in the dark sector decays to two dark matter, that works, right? But it has to happen at the very early universe because you have to redshift the energy to have a non-relativistic dark matter. So this guy has to be long-lived or stable.
Okay.
So of course, the dark sector could be very complicated. You can have decays of particles in the dark sector into dark matter, but then at the end,
okay,
you have to have a...
Great, thank you.
Yeah, long-lived, yeah. But yeah, it's true. Here I'm basically focusing on the simple scenario where you have a single dark matter, so no asymmetries, but maybe the natural thing is to have a look at the standard model, right? So it's a complete mess. So the dark sector may be at least as complicated as the standard model. So several components. You can have confinement, right? Bound states, like dark pions. Yeah. Here I'm only concentrate on single particle dark matter with no asymmetries. But yes, in principle, life could be. I don't know. We'll discuss multi-component dark matter at some point. Yes, but a couple of comments on Saturday. No, Friday. Yes. Question: did the Kafir show you this kind of thing? Did he discuss the evolution of the universe? Maybe not. Okay, good. So why it's interesting or it's very important to discuss about the history of the universe? Basically because dark matter was created in the early universe, right? So of course we have to, if we want to study dark matter, we have to have like all the particle physics under control. And when I'm talking about particle physics, what I have in mind is like the mechanism, this line, right? This basically corresponds to how dark matter was produced. The misalignment, discussed by Kafir, it could be a WIMP, SIMP, FIMP, Elder, Cannibal, Axion. All that is really refers to the particle physics, how the dark matter interacts with itself, how dark matter is interacting with the other components of the dark sector of the standard model. Okay, that's kind of under control. However, dark matter was produced in the early universe, so we have to have also control on the cosmological evolution of the universe, right? That's the other key point on the dark matter genesis. So history of the universe in one slide. So we expect the very beginning to be inflation. And why inflation? In a nutshell, what we observe now is the universe flat, right, from one side, is homogeneous and isotropic. So we need an era of, okay, what inflation says that we have this era of exponentially fast expansion of the universe. So basically, the energy density is dominated by this inflaton. So we have this exponentially fast expansion. At the end of inflation, the universe is basically empty. And why it's empty is because even if we're not changing the number of particles, say standard model particles of species there, the size of the universe is growing a lot. Right? So you have you have a box with a given number of particles. This box expands exponentially fast. So at the end, the number density, really the density number of particles over the volume is super small due to this super big, super fast expansion. Right? At the end of the inflation, what you have is the universe energy density dominated by the inflaton, these mysterious particles. The universe kind of empty. You have to transition from a universe dominated by inflatons, so energy density in inflatons, to energy density in standard model, right? You want to create the thermal plasma, you want to create photons, standard model particles. And this era is at the end of inflation, is basically reheating. They put this artistic view here. So reheating is basically this transition between a universe dominated by inflatons to a universe dominated by standard model particles. So how this reheating era happens, we don't know. It could be just the decay of the inflaton. You could have scatterings of inflatons to generate standard model particles. We can have very complicated processes, but the idea of reheating is this transition from only energy density dominated by inflatons to the creation of the thermal plasma and the onset of the standard model radiation era, right? At some point, then you have basically BBN, when you have, say, when the universe is like 1 minute, 3 minutes old. So BBN again is so this Big Bang nucleosynthesis is the creation of nuclei heavier than hydrogen. So you have, as usual, helium, deuterium, lithium, tritium, beryllium, that are created when the universe was, like, say, minutes old. All the other heavier elements are created not at BBN, so the Big Bang nucleosynthesis, but really the star nucleosynthesis with supernovae, but at much later times. We have also then the creation of the CMB, right, when the universe was 380,000 year old. And then, okay, you have, like, you see, modern universe creation of all the structures that we see. So the important thing is that dark matter was produced in the early universe. We don't know exactly when. So dark matter could have been produced during inflation or during reheating. We don't know exactly, so we have to have a kind of control. We have to try to have control or try to bracket all the uncertainties in this early universe dynamics. Right? It's completely uncertain. In particular, before BBN, so the first minutes of the universe are completely uncertain. So we know that the moment of the BBN, the universe was dominated by standard model radiation, and we know that from that moment, the standard model entropy, total entropy was conserved. However, before the onset of BBN, so for instance, between the end of inflation and the beginning of BBN, uncertainties are maximal, basically because we have no observation. So in these lectures, of course, I will focus on the particle physics, cosmology, but also try to emphasize what is the role, what are the uncertainties, in particular during reheating, or if you can have non-standard cosmological evolutions of the universe before BBN. And again, why? Is because if we want to compute, for instance, the dark matter abundance, if we want to understand the properties of dark matter, cosmology plays a fundamental role, right? So maybe it's a good moment to stop. So are there questions or comments? Yeah. Thanks.
Very good that you finished before the...
10 minutes.
That's perfect for questions, yes. Yes. So 1, 2...
There is a thing I never understood, that when you go to cosmology, we have a ratio 5:1 of dark matter versus baryon. But when you are like in galactic clusters, so on, usually we have much more dark matter than baryons, like 10, sometimes hundreds of times. Usually, I think in galaxy clusters scales. So why do you have this difference between this ratio in different scales?
Yes, yeah, this 25% or so is really an average, right? At very high scales. What is it here? But of course, you don't expect this to be homogeneous, this. Right, for instance, the example you just gave. But it's really an average in the whole universe. Yeah.
Okay, so it's really the structure of the universe on large scale, like.
Exactly, yes. This is really a large scale, a cosmological scale. It really comes from the CMB. Yeah.
Okay, but do you have like simulations showing that this is consistent? Like you make a simulation in this scale, it matches with the other scale?
Yeah, like, but wait, for instance, remember I put here the NFW profile here? So that tells you how the dark matter is distributed in, for instance, in a galaxy. So it's not constant. So from there you can see that you don't expect this ratio to be constant in, yeah. Yeah, but it's not. Really, this is at the cosmological scale, large scales. Yeah.
Okay, thanks.
A very good picture I'm going to use in the future, but with a sponge cage instead.
You can put a tapioca.
Yeah. I mean, I told you that I don't know too much about dark matter. So can you give me a good argument to believe that is a really particle, not a modified gravitational? model?
Yes, I want to make that comment at the very end. It's true. I mean, after all like the hints that we have to dark matter comes from gravity, right? So we could have modifications of the Newtonian gravity because it's a really classical level. Maybe it's more natural, right? I don't know. We are particle physicists, so of course we push to for this
it's
option.
funny to propose new
However,
particles, right?
as far as I understand, you can all this what I explained at the very beginning could be explained these theories of Mond, for instance. However, well, like one by one, you have to tune not even the theory, your setup to tackle one. I mean, at each different scale, but you cannot understand the whole picture with Mond, as far as I understand. So that's one thing. Other thing is that I don't think you have a theory of Mond, of this modified gravity. So it's like an effective thing that you put and it try to fit you can adjust the parameters to fit it. But I mean, from a very pragmatical point of view, I think it deserves to take a look on these Mond theories. I will not spend a single second on that personally. But I mean, we need. I mean, we will be convinced of dark matter if we need to detect, right? A detection other than gravitational. Because if we want gravitational dark matter, I mean, I gave you all the detection, right? So dark matter is there. We observe it in the cosmos. But as a particle physics, we really want to produce at colliders, right? So it's better to be at the GeV or TeV scale. Yes, I don't know if someone wants to comment about Mond.
Okay. My second question is, you told about the production of dark matter, right? Why can't it be kind of a fundamental field that was always there? Like the Higgs. The Higgs didn't decay from any field. It was always there. Why dark matter must be produced in some point of the universe? Why can't it be kind of fundamental
Well, you
field?
have the fixed field because you can also have produce the Higgs quanta, right? So you can produce at the
okay.
at the LHC.
Okay, I see. Okay, thank you.
And coming back to the question before, for some reason, I don't know exactly why, I felt like the concentration of dark matter in the whole universe should be bigger than inside, proportionally should be bigger than inside galaxy clusters or whatever. So can you give me perhaps an intuition or explanation on why, for example, on average, you should expect less dark matter proportionally than on galaxy clusters and whatnot?
Well, you can think dark matter gravitates, so you expect to have like clumps of dark matter. I mean, think about baryons. Forget about dark matter. Think about baryons, right? They are not uniformly distributed in the universe, right? There are voids. You can feel there are stars, planets, right? Black holes. So were you expecting dark matter to be uniformly distributed in the universe?
No, it's because it should clump, sure, but I mean a lot of it is also like on large structures, very sparsely distributed and whatever. And for some reason, I thought that the baryons would clump more in these dark matter regions than dark matter itself for some reason.
Well, typically what you expect, I mean, or maybe what embedded simulation is telling you is that you first start collapsing dark matter, so you form this potential well, and there
and then
you
afterwards
have baryons,
the baryons
exactly,
go and
going there.
Yeah, that makes sense. Yeah. Okay, thank you.
Yeah.
Yes. So I'm not an expert, but I believe that this is a similar question that was just asked here, and I think part of the answer is that you know, in the initial plasma, baryons actually have a restoring force because they interact, whereas dark matter just falls in. So I believe, I'm not sure, not totally confident, but I think that in the initial formation of gravitational wells, dark matter gets more concentrated. In any case, I think it is, one thing I'm more confident about is that n-body simulations are able to reproduce this together with CMB-type initial conditions. So if it's not exactly that, it's something to do with the dynamics of either the initial density formations or how they subsequently evolve.
Yeah, exactly. Thanks.
And in addition to n-body simulations, there's simulations with baryons as well. So you can see galaxies forming. More questions? Comments? Okay, so if not, let's thank Nicolás.
Thank you.
And coffee break.